All right, we are up and going. Hello, everyone. My name is Mr. Barden. If you don't know me, I haven't seen any videos before this, might recommend checking out a few other ones. I do this kind of as a ongoing series about a bunch of different things for the Programming Digital Media course that I teach as part of my work here at LSU. This PowerPoint is going to go over a lot of things used in the physical computing unit of that class. So again, I recommend checking out some of the various previous resources if you're just diving in. But if you just want a quick tour over, what a bunch of physical computing things are, how to use them, how this still might be useful for you. What I'm going to go over here is just, again, a lot of the very basic stuff, how electricity works on a general level, different kinds of components. We'll be using Arduino for this, things like that, just of that nature. So definitely check this out if you're in the course, or if you just feel like being useful. This could be useful for you. I'm just going to be going through these slides, and I'll have a link to this and any other important information down in the description below. So as you're going through this, if you feel you don't quite get something, maybe you want a little more explanation about a what, why, or how, put that down in the comments. I'll respond, answer those as best I can whenever I see them. We'll go from there. If you learn something and enjoy the content, do all the YouTube stuff, like, comment, subscribe, blah, 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 blah. And let's just jump into it. So, like I said, these slides will be in the description below, so if you want to have these for your own, you can go grab those. Physical computing is, well, what it sounds like. It's utilizing a computer in the physical world with real-world parts and elements. Up until this point in the class, we've been doing strictly code stuff with virtual things and electronic files and ones and zeros and stuff like that. But this is going to be, will be code, but it'll be responding to and utilizing real world things. So there's generally kind of two sections to it, the physical and the computing. So the physical things, we have, actuators, stuff that does something. Resistors are going to be your best friend in this class. Transistors, capacitors, it ultimately depends on what you're going to be building in your sections. But we'll kind of give a general overview and talk about the most common things throughout here. You need, believe it or not, you need electricity to make this electrical circuit work, so also power sources. Most of the time for this class, you'll use the USB connection from the Arduino to your computer, but you could hook up batteries or to a power outlet with a wall wart and things like that. You may also see several diagrams like this, or maybe it's more of a picture diagram with little graphic representations of all the components and the wires. It depends on what you're looking at. This here is going to be an Arduino. This is an actual Arduino brand one. They have a bunch of different types of boards, but this one, the Arduino Uno is what this model is called, is probably the most common one out there for a lot of this stuff. You can connect it again to a USB or the power supply like I mentioned, and once you've done that, you can run the code that you would have written in a separate program. I'll talk about the code in a different video, but it's based off of the C programming language, so it's got a lot in common structurally with the JavaScript we've been using in this course, but there are some important and distinct differences that I'll get into in a separate video. But basically, you can kind of in tandem build your circuits, build your code, and then through the USB connection, you will flash it or send it to your Arduino, and this is the CPU that's in charge of everything. And then you can connect the various components to these little pin headers in order to have it respond and do stuff. Come on, there we go. So before we get into that, though, we should probably discuss what is electricity. Now, you more than likely utilize this, every day, especially if you're taking this course because, it's all computer coding, but, you don't just plug something into the wall and then it magically appears. essentially what it is just the flow of electrons, and these are very, very, very tiny, negatively charged, is what they call it, particles. Uh, and they move around a bit. You know, if you've ever seen a diagram of an atom, you'll know that in the middle we have the nucleus with the protons and neutrons, and then around it, kind of in a big cloud, are all of the electrons. But because these electrons are moving around in a cloud and different kinds of energy levels and all that stuff, sometimes they bounce off and transfer, and we can direct that in a stream of electrical current. So we'll get a bunch of electrons together that makes a electrical charge that can then travel to different places. If you've ever seen lightning, this is again those electrons moving from the sky to the ground. Uh, right, and that's essentially what we are controlling with electricity. Uh, this electricity will travel through everything, um, but not always the same rate. So if you ever heard the phrase "water conducts electricity," well, I mean, water allows electricity to flow through it very quickly and efficiently. Things like metal and water, like I mentioned. Those are some really good conductors, but other stuff, maybe, well, air to a degree. Um, what was I thinking? Rubber is a big one. The human skin, maybe a little less than some of those, but those are all insulators. They help block that flow of electrons. Uh, Again, these all vary in terms of what's more effective than the other, but just know that sometimes you can send electricity from A to B very quickly and efficiently. Sometimes it takes a lot more energy to get that going. All right. So once we get that electricity kind of moving around, that's the key thing, is this movement of the electrical current. There are three main parts that come into play for every electrical circuit, and that is the voltage, the current, and the resistance. All right, these are important terms. That's why they're all in red, and we're going to go through each of them on the next few slides. So, I like to compare this to how water might flow. Okay, because again, we have to have this stream of electricity, this current that's moving around continually in order to have a circuit, right? A circuit is just like a loop. So, again, I like to think of this as water. So let's look at this diagram up here. Um, we get a few different things. So the water itself that is flowing, the amount of water, the green, how much flow is there, that's the current. Okay, so if you have just a little trickle of a stream compared to Niagara Falls, one of those has a lot more flowing through it, so a lot more current than the other. That Niagara Falls in that example. And again, if you have a lot of electricity running through compared to a little, that first one's going to be a lot more potentially dangerous. All right, the pressure. All right, so this is how fast, how hard that electricity is moving. That is the voltage. In these diagrams here, basically this water is moving uphill through some means. Um, in this one, it's a water pump. It's moving up, and then it's falling down. This actually, the water moving with a certain amount of force, that is the voltage. All right, and then once we add the electricity, the energy, we're pumping it back up to fall down, and that's what that power comes in. That electricity is doing that work. Um, and then lastly, just maybe the thickness of the pipes or rocks in the river or bins, anything that impedes that flow is the resistance, and we're going to need some resistance. Otherwise, the electricity is just going to shoot through everything super fast, super strong, and it could potentially damage various components. So when we build these circuits, we have to factor in certain amounts of resistance in order for things to work properly. All right, so voltage. I've got this diagram up here as well. Artist is in the image. again, this is basically just saying what I've just said. So the voltage is the force that's pushing the electricity through the circuit. Uh, Okay, so if we have a big mass of electrons, that's going to be very negatively charged. And if you've ever held magnets to each other, you know, the positive uh, draws the negative, so it's going to, and they draw to each other, so it's going to force itself to kind of loop through. That's the voltage, essentially. And we measure this in volts. So again, that is what is driving the current through everything else, through the circuit. The current itself, we measure this in amps, and this is, again, the amount of electrons flowing through the wires. So, again, the voltage is pushing the electrons through, the amount of those is the current. And the resistance, which is measured in ohms, um, is kind of anything that is, you know, blocking that current. It can also be called the load. So if you see um, that phrase, you know what that is. I tend to refer to resistance, uh, and that's, again, that's impeding the current intentionally, and so that's making it harder to squeeze everything through. Okay, so those are some of the main parts of electricity. We get the power sources, whether this be, you know, batteries, plugging something into your phone over USB, plugging it directly into the wall. I do want to stress, for this course, you should just plug your Arduino into USB to your computer. Um, or if you really need to, you could use like a small like a 9 volt or a AA battery. You don't want to plug it into the wall. That's just, it's not as safe. And if you're still learning what you're doing, which is what you as a student in this class are, you don't go plugging in and making circuits and short. You know, you could actually accidentally very drastically hurt yourself using the voltage coming out of the wall as you're building your circuits. And if you accidentally get, you know, something backwards, it could pop and blow up. You could short it out, or you could, you know, touch a thing and get really badly shocked. So you want to use these power sources that are a much lower amount of current and voltage. So again, using things like the USB port, that's what we want. The power sources, they serve a very specific purpose, and that is to move the electrons from the low energy side to the high energy side. It energizes the electrons, so it moves through the circuit. All right, so that's the, going back a few slides, that's the, go away. That is the water pump in this analogy. That's the, we don't really know how in this diagram that it's pulling it up, you know, pulling it uphill back to that top part of that circuit. That is what the power source does. Um, so again, it's kind of creating this electrical pressure, um, and then normally the electricity kind of moves from that high energy state down to the low state, and that is the circuit. It moves from high to low, and then the electrons get re-energized back to high, and we travel over and over again. I keep doing this looping motion kind of with my hands because, again, that's the whole thing. The circuit, we're just moving electrons in a circle, but in a looping pattern through all the wires and the components, in order to use this power in some way. Um, all right, the low side is the negative or the ground. This is going to be an important tool to have here, with the high energy side being positive or plus. Um, Power sources will tell you what the difference between the positive and negative sides are. If you've ever seen a battery, it'll usually have this etched on it, or they'll be very clear. You know, one terminal's bigger than the other, or one side has a bump and one's flat. It varies depending on the battery shape, but they all have a very clear positive and negative side. Okay, so why did we go through all of that about voltage and current and resistance? Well, we can use this thing called math in order to work out the various relationships between all of the stuff. And there's a formula here called Ohm's law. When I write it, I tend to do it with the voltage equals current times resistance, and that's the relationship between them. But you can see it written in any of these other combinations of the current is equal to the voltage divided by the resistance, or the resistance, and so on. Depends on what you need to work out. A lot of times it may be the resistance. So you know how much voltage and current you're working with, how much resistance do you need for X and stuff like that. For a lot of the simpler things in this course, you may not need to use this all the time, but it is very useful when working out your electricity. Just think about the relationship between, okay, if I increase the voltage, what's going to happen here? We'll use a thing called variable resistors, so the resistance will change. So if we increase the resistance, what's going to happen to the voltage or the current, since those will stay the same, and we don't gain or lose any electricity. It's a closed system. So if we adjust the resistance, what's going to happen? That will come in handy. All right, power. So if we can talk about power by combining specifically the current and the voltage, and that's measured in watts. You may have heard of like a 60-watt light bulb, and there's the formula right there again. Watts or power is equal to the volts times the amps, so voltage times current. I don't know why that one's an I. I wasn't there at the meeting, but that's the equation for that one. Okay, circuits. All right, so I said before that a circuit is just a closed loop containing a source of electrical energy and a load. In this case, we have the lamp and the battery. Electrons will normally flow from the high energy side through the circuit down to the low energy side, um, and they repeat that over and over and over again. Sometimes you'll see a little diagram like this indicating that directional movement. You don't always see it though, but if you do see it, that's what that little thing is. Um, the load, the thing that's plugged in, these things do stuff. There's a wide variety of components that we'll get into, mostly in another video. I'll mention a few of them here, but they do something, whether it's make a light, to make a buzzer, or turn a motor, or whatever. They do a thing. So they take that energy and use it to do something, and then pass on the now spent electrons back to the negative side. The electrons then get re-energized in the power source and go back to the thing that's doing something. In this case, it's a lamp. So I want to go back real quick and discuss these bullet points. So the bullet points that were just on that last slide proposed a question of, what if the resistance in a circuit was 0? And I mentioned a little bit of this before. Well, if we look at this equation, the current is going to be equal to voltage divided by the resistance. Well, if the resistance is 0, the current is going to equal the volts divided by 0. But you can't divide something by 0. It's physically impossible. And this is just a mathematical way of pointing out that you will have what's called a short circuit. That's bad. So basically, if there was no resistance in this system at all, the electricity, the electrons would transfer from high to low, but they wouldn't have expended any energy, so they would have been at the, gotten back to the negative with the high power, and then they got more. It's bad. The electricity circuit does not work without some inherent resistance in the system. You don't want to short circuit stuff. So if you've ever I'm not saying do this, but maybe you've gone in and had to like jump a car. So you attach your jumper cables, one to the battery, one to ground, and if you touch them, they spark up, and that is the circuit shorting as the electricity is just jumping and going straight to ground to dissipate. That's not a good thing for the context of this course. And again, I'm not saying go do that. That's not a great thing to do because you can get shocked. Okay, So we use conductors, getting back on track, to move this electricity, and wires, um, to move things around. So wires, they don't have to be, but generally they are insulated, so that way we can connect the metal bit from here to over there and move the electricity in a path. Kind of like if you've ever used a water hose or a water pipe. It's used to funnel the contents to a very specific place for a very specific reason. So I have a little few hypotheticals. Normally I'd, give my students a second to, answer this, but I'm just going to talk about them as we go along because this is a video. It's not a very interactive format. So would this hypothetical arrangement work? The answer is no. So what we've got here, we've got a battery and we've got a bulb and a wire connecting them. But remember, we have to connect this in a repeating circuit. All right, the electricity has to be able to flow in a repeated pattern. Actually, we'll go that way, according to the diagrams. So because the wire isn't connecting this down to the back end of the battery, it's not forming a complete loop. So the electricity would not flow. Um, would this work? The answer is also no, because uh, again, we've got our bulb and we're connecting all of this here, but we're connecting two things to the positive end of the battery. This still just wouldn't flow because we're not connecting to the negative end of the battery. Um, this one, however, would, because we are connecting the positive end to the battery, and then, the positive end of the battery to the bulb, and then that's going around back to the negative end of the battery where it gets energized, and then it goes over and over and over again, and we'll get power. How long that works, I can't say, and this would not be a very practical use, but this is a functioning circuit in the physical world. All right, here's that concept. It's that completed circuit. It's going, repeating over and over again. All right. Uh, we'll use some diagrams to illustrate this. Sometimes it'll be a kind of more graphic representation where all the parts look like they're real counterparts and you can see the wires connecting. Other times we may see this, where it's showing the path flow through the wires and the various things. And different symbols represent different components. So here's a battery. So we go, negative to positive. The current's going to travel through here. It's going to flow, around the bulb, around the loop, and go through. So, and when it's doing that, that's when the bulb is getting that power and doing stuff, and then it moves through the circuit back to ground and repeats. So this is the same as that. It's just this is a lot more cleaner to look at than this. All right, but just know that the electricity generally is moving, the current's flowing. Okay, so that's the first chunk. A lot of how electricity works, why you might why we need to build it in circuits, blah blah blah. I'm going to talk now a bit about the various components that we'll be using in this class. There's the main three: resistors, switches, and then LEDs, and then there's a few other ones that I will mention as we go. The first, and debatably most important, are the resistors. Again, these add that resistance to the electricity circuit in order to kind of slow down that flow. I'm approximating exactly what's happening in order to make things a little more manageable. We don't want to blow out components, things like that. There are generally two different kinds. The first are fixed resistors, and here's what a few real world ones look like. And again, the current would flow through these leads right here, these wires, into this part in the middle. And this is just made up of stuff, different things, and this just impedes that flow of electricity. So the more resistance in the resistor, so this one's a lot more resistant than some of these small ones, the more it's impeding that electrical flow. And we can see that with these diagrams if we use those kind of wireframe ones here in that circuit diagram. Sometimes it's the zigzaggy, sometimes it's the rectangle. But these are always the same. So like these don't change their resistance. So if you needed to change it, you'd have to take out the old one and put a new one in. This is different than a variable resistor, and here's a few symbols for that. I usually use number 2, but you can see them in different ways. Basically, it's a resistor with an arrow of some kind, but I usually use number 2. Um, anyways, but these can change the amount of resistance. Um, some of them are dials, or what's called a potentiometer. So as you turn it one way, it increases the resistance. As you turn it the other, it lowers it. Um, Basically, there's just some material on a wiper, and as we move it, of course, the electricity is flowing through more of it versus less, so we can get more or less. Same thing with the slider here. It's just in a different position. It's going to resist it more versus less. So that can be useful for making the amount of the voltage running through a thing change. So maybe you wanted to change the brightness of something, or that's going to be the example I use. But there's a lot of applications by just being able to change the amount of resistance in your circuit. So let's go back to the fixed resistors, because this is going to be something we use a lot in the course. They look, kind of like this. There's just a little blob on a wire. So in order to tell them apart, we have this code, this standardized code of colors that we can put on the resistors. So in your kits that we have, they're all rated for a quarter watt. That's kind of like a standard. Um, but then we have just this little blob on there. Sometimes they'll be blue, sometimes they'll be brown, but that's usually the majority of them. So the amount of bands can vary, and that depends usually on like the resistance, or I'm sorry, not the resistance, the tolerance. So some of them have more or less variance from resistor to resistor. Um, that's essentially what it is. But then this tells us how to read the bands. So as you look at the band, um, the first one is going to tell you the first digit of a number, and then the second one's the second digit, and so on, until you get to the last, the second to last band. And this is going to be a multiplier. So we're going to multiply this first number we got by some amount, and that is the amount of ohms that we have. So again, this one that is 27,000 ohms, we get red, which is 2, so 2. This purple, which is 7, 2, 7, and then this orange. I guess it is orange in real life. This diagram makes it look a little more fleshy colored, but that's multiplying it by 1,000. So 3 zeros. So 27,000 times 1,000, 27,000. 15K here. So we get first band is 1, second band is 5, third band is black. So 150 times 100 is 15,000. Last one, again, just going through the process, we've got here 620 kilo ohms. So we get 5 is the first, or I'm sorry, 6. The blue is 6 for the first one. Cool. The second one is red, 2, 6, 2. 0 is black. 6, 2 times 1,000, orange. There we are. I will be said, with these more and more bands, you tend to get more variety, and this is telling us a few other things with the extra bands. But generally, all the ones we'll have in this class will be the 4 and 5 band resistors. I very rarely come across these in what I do. You may, if you do electrical circuit designing, have more use of these than I do in my experience. But this is the color code. So again, you can, first digit, second digit, a multiplier, or in some cases, divider value, but I very rarely see the dividers. It's mostly the multipliers. And that's that. So we've got this one right here. So let's go through it. We'll go from side to side. There's a very hard to see gold band right there. So let's look at this again. So we've got kind of a pink, brown. I guess orange is what I would call that. What does it say? It says that. Okay, this I didn't choose that image. That one says red. I wouldn't have called that red, but okay. Okay, so red, brown. So red is 2, red again, 2, 22, brown, 10, 220 ohms. 22 times 10. There we go. It takes a little bit of practice. I usually keep a diagram like this by me when I'm working with resistors, just so I can double check it before I put it in there. Okay, switches. So a switch. Moving on to the next thing. These are used to route or just pause the flow of electricity between A and B. So here's a kind of what you would see in the circuit diagram. So you can see that it's not connected until you push it down, and then it connects it, and there you go. So basically, the leads get connected, to power, ground, and it passes it along, and so forth. There's what's called a momentary and versus like a toggle switch. So these switches over here on the left of the screen, they're basically switching between. They're in a binary state. It's A or B. There's no other thing. It's the circuit's either going to route something to A over here or B over there. There's no other option. This is different than the push button. Uh, the momentary push button like this, sometimes you can get ones that click and hold it, but basically you press it, and that is what completes the circuit. There's no routing and switching. It's just press it, it connects all the paths, let go, it stops it. So again, that's why we get like an on-off switch versus a push to activate kind of thing. That thing that becomes a little more clear once you start using the buttons. If you run into a tilt switch, they look kind of like a little tube with 2 leads pointing out, and basically when you tilt it far enough, a metal ball connects it, and electricity can run through the contacts. So open versus closed. Okay, moving along, because this is already a kind of long video. Diodes. So a diode it only lets electricity move through it in one direction. There's a specific positive versus a negative side. It will not let electricity flow the other way. So if you have your diode backwards, it's not gonna work. You can also potentially make it, pop and blow up and do stuff like that. An LED is a specific kind of diode. It stands for light emitting diode, and they emit light. And basically, the electricity goes in one side, and then as it travels, through the diode, it loses a bunch of energy, and that's given off as light. All the LEDs here and most diodes are very clearly marked what's the positive and negative. So if you have a diode that doesn't give off light, it'll have an indicator on the component. But for the LED, usually there's a long lead, a long side, and a short side to the wires coming out of it, the leads. So the anode is the one where the electricity is coming from the positive side, and the cathode is the shorter lead that is sending the electricity to ground. So that's how you work it out. So if you put your LED in your circuit, it doesn't work, try taking it out, flipping it around in the circuit and putting it back in. That may fix your problem. Again, it could also potentially pop the LED and just ruin it. But usually they don't use a lot of current, and they use very low voltages. So it's a great and efficient way to make light. For a lot of the higher power ones, they can generate a lot of heat. So that is just a fact of them. But for everything in this class, we won't be using enough power for that. But it's just a fun little factor. Okay, now I'm just getting into the extra nits and bits and stuff. So a capacitor essentially gathers up an electrical charge and dissipates it at a later moment. Um, so they're rated by how much power they can store. They're measured in farads. Here's this one does 1,000 microfarads, is what it's saying. And so again, it builds up a charge and then can send it out. They can be very useful for different things. So if we're doing some stuff with motors, you'll see that these come up to gather up that charge to send it to the motor to do something. A transistor and a relay are different kinds of switches, essentially. So basically, a normal switch is something that you, as the user, would interact with to move. So you press the button, flip the switch, whatever. But a transistor and a relay switch based off of electricity. So, for example, you have a relay that's maybe it's open until the electricity runs through it, and then it closes. And then when the electricity stops, it opens again. It can be useful for certain things, and that's just some of the more common ones. There's a wide variety of components, and if I go through any more of them, it would kind of just belabor the point for the purposes of this video. uh, on this page of the slides, there are some more of those symbols for the different uh, types of components you might run into. So, power sources, batteries, voltage nodes, LEDs, um, switches, all that kind of stuff. I'm not going to go through all this in detail. If you want to look at a specific one, you can pause this. But there's a variety of diagrams that or symbols that we can use for these diagrams. All right, this slide is going over the various names that you might see in the circuit diagrams by letters. So if you just see like R1, that's resistor 1 in the diagram, versus U2, that's an integrated circuit chip number 2 on the diagram, and so on. So it kind of depends on what you would be building, but you may see in a diagram these letter indicators. Okay, so here's an example of, we have a battery 1. The positive is marked. It's a 3-volt battery. It runs through resistor 1. There's the symbol that is 220 ohms, and then through LED 1, and that's a red LED, before going back to ground. You may have heard this phrase before, but whether a circuit is parallel or in series. If something is in series, the circuit, the power is going to go through one one load here to another, and in order before going back to ground. If something interrupts the series, the whole circuit is broken. This is different than in parallel. So basically, what's different is that uh, each of these is forming their own independent circuit. Each light bulb fixture here is independently connected to the positive end of the battery and to the ground of the battery. So even though we pull the light out of one, the other two still work. Unlike the series where we pull out one bulb, then the whole thing stops. This used to be how they did a lot of like Christmas and holiday lights, and it was a major pain because if you plug it in and they don't work, you have to go through and find the sometimes single bulb in your strand of 200 light bulbs, to find the broken one. Uh, Nowadays, most of them are done in parallel, so that way you can it'll work, but just that one will be out and you can replace it. Um, that might be where you've run into this kind of thing before. Here's just the diagram. Here's the series here. Um, Battery here. It goes through one resistor and then the other. So that is, these resistors are in series. It comes out of one and goes to the other. Compared to parallel, where it goes through one and the other independently. Okay, we are approaching the end of this PowerPoint. When we start building these circuits, we'll be using what's called a breadboard. You'll find these in most of your Arduino kits, or they can be ordered online for relatively cheap. So basically, these have little holes in them that make it very easy to push the leads of our components into here and build a circuit. So basically, these are all connected in a row right here. So if I plug the battery into right here where my mouse is, everything on that horizontal row will be connected to that power source. So I could branch off and do a bunch of different things uh, from there. The way we tend to line it up, if you were to take your breadboard and flip it over, you would see this metal that's acting as a conductor that goes along the length of the breadboard, and then it's a whole bunch of these different horizontal ones. So we can put in a bunch of things and connect it. There's the common power and ground along the sides, and then whatever we need, it's a little more isolated. Just note that there is a divider in the middle where the traces don't connect. So this side is independent of that side. It can be a useful tool, but it's easy enough to bridge if you just don't need the gap there. Um, I think this is a little more clear once you get into your class and see the component. Um, but I think it's relatively straightforward. These horizontal lines all share the same. They're all connected, and then the vertical ones are as well. So sometimes they get small, sometimes they get big. But here we are, connecting positive and ground and all the components. This is also using it. This is a little. Is it a motor or a speak? I'm not 100% sure, but it's getting stuff from the potentiometer up there. Okay, wires. So like I mentioned, the wires are conductors. We can connect it from A to B and it'll flow the electricity through it. There's going to be a variety of colors that you have access to. Uh, these are sometimes called jumper wires, jumper because we're plugging them in and connecting them. But there are a few conventions for what certain colors are used for. So red wires, again, technically there's no difference if you take from your kit and plug the blue wire compared to the red wire, like it's going to function the same way. But if you use some of these conventions, other people looking at your circuit will know what the heck is going on. In actual electrical, if you're building and wiring stuff, these conventions for what is what are very important, because otherwise some person will go in to fix something, and if it's not wired up correctly with the right labels, they could hurt themselves by cutting the wrong thing and there's still power there, or it'll get wired up incorrectly and it'll short the whole circuit and blow the fuse. It's very important that you follow this convention for wires. So red is used for positive power, the power coming from the power source. Black or green are used for the negative power. I've also seen white, but black and green are the most commons to use. So I basically only use red and black for those unless I don't have a choice. And then from there, it kind of is open ended. I try to group mine up by what I'm doing. So like all of the the lights would get the orange LED, and the potentiometer might get the red, or not the red, the brown or the blue or the whatever. It can the big ones are the positive and negative, being red and black or green. And we can go from there. There are other general rules, but that's the big ones. Like I mentioned, the breadboard left and right sides are not connected. There's this gap going down the middle. So you'll have to connect them, connect power to both sides. And the easiest way to do that is to connect one side to your Arduino's power and ground, and then just jump them, jump it over like this on the other side of the breadboard. So you just want to connect positive to positive and negative to negative, and now both sides of this breadboard are wired up. All right, so wiring from a circuit diagram. This is the kind of diagram I mentioned that I'll use sometimes in my teaching compared to this one. So let's just look at this here. So we've got a battery here. We go from the positive end to a resistor, to a switch, to an LED, to ground. So let's just follow this pathway here using the real world components. We go start on a battery. We have the positive end of the battery going into our breadboard to the positive. So that's going from positive to a resistor, to a switch. One end of the switch isn't connected to anything. We see that. The other one is connected to the LED. And then we go from the LED to ground. So this serves as an LED with a switch that turns it on and off. Example, wiring. So this will be a thing if I was in front of you teaching this in a class. I'd say, now draw this, and there you go. But I always forget this is the end. Well, more or less the end. But basically, you would just draw this diagram and get the power, and it goes in parallel through these two identical things. So, you would see the same. It's going through the LED, through a resistor, through a switch to ground, twice. And then we would just get some more practice problems if you were in the class. But since this is a video, there's kind of no point. I'll put each of these on the screen if you want to look at them and try to solve them on your own. But I'm not going to go through them right here. And 3. All right, so that is going to wrap this up. So like I mentioned, I'll have all the relevant stuff in the description down below. If you found this useful, like, comment, subscribe, blah, 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 all the YouTube stuff. And that's going to end it from me. I'll come back in a future video and we'll talk a bit more about using Arduino and building these circuits and making them respond with the, both respond to and with the code that you will write to put on the controller. And that's going to end it from me. So I will see you all the next time that I see you. Bye.